Characteristics of common base CB. In this lesson, the learner will be able to describe common base configuration, explain characteristics of common base configuration. Previously, we have seen the construction and operation of BJT. Now, we can see common base configuration in detail. The common base terminology is derived from the fact that the base is common to both the input and output sides of the configuration. In addition, the base is usually the terminal closest to or at ground potential. In this configuration, input is applied between emitter and base and output is taken from the collector and base. All current directions will refer to conventional, that is, hole flow rather than electron flow. The result is that the arrows in all electronic symbols have a direction defined by this convention. To understand complete electrical behavior of a transistor, it is necessary to study the interrelation of various currents and voltages. These relationships can be plotted graphically, which are commonly known as the characteristics of transistor. The characteristics of transistor in any configuration are input and output characteristics. Input characteristics is the curve between input current IE, emitter current, and input voltage VEB, emitter base voltage, at constant collector base voltage VCB. After the cut-in voltage, the emitter current IE increases rapidly with small increase in emitter base voltage VEB. Now, let us plot the input characteristics for VCB is equal to 5 volts. After the cut-in voltage, 0.7 volts for silicon and 0.3 volts for germanium, the emitter current IE increases rapidly with small increase in emitter base voltage VEB. It means that input resistance is very small because input resistance is the ratio of change in emitter base voltage to the resulting change in emitter current at constant collector base voltage. This resistance is also known as the dynamic input resistance of the transistor in CB configuration. When we increase collector base voltage to 10 volts with constant emitter base voltage, the emitter base current increases slightly. For VCB equal to 5 volts, when VEB is 1.5 volts, then IE is 1.2 mA. When VCB equal to 10 volts, when VEB 1.5 volts, here in this stage, IE is 2 mA. Thus, it can be observed that there is slight increase in emitter current IE with increase in VCB. When reverse bias voltage VCB increases, the width of depletion region also increases, which reduces the electrical base width. Due to reduction of the electrical base width, now there are more charged particles per unit area. This increase in concentration of charge carriers causes more diffusion of electrons from N-type base increasing emitter current slightly. Early effect or base width modulation. The decrease in effective base width with increasing reverse bias of collector base junction is called as early effect or base width modulation. It is the curve between collector current IC and collector base voltage VCB at constant emitter current IE. The output characteristics have active, cutoff, and saturation regions. For the operation in the active region, the emitter base junction is forward biased while collector base junction is reverse biased. In this region, collector current IC is approximately equal to the emitter current IE, and the transistor works as an amplifier. If the emitter current is 0, the collector current is simply ICBO as shown in figure. This current is so small in magnitude compared to the vertical scale of IC that it virtually appears on the exaggerated scale for understanding purpose. The region below the curve IE is equal to 0 is known as cutoff region, where the collector current is nearly 0. The saturation region is that region of the characteristics which is to the left of VCB is equal to 0 volts. There is an exponential increase in collector current as the voltage VCB increases towards 0 volts. In the active region, the collector current is essentially almost constant and the graph is almost parallel to x-axis. The collector current IC is almost independent on collector base voltage VCB, and the transistor can be set to work as constant current source. This provides very high dynamic output resistance. Dynamic output resistance is the ratio of change in collector base voltage to the resulting change in collector current at constant emitter current IE. As IE increases, IC also increases. Thus, IC depends upon input current IE but not on collector voltage. Hence, input current controls output current. For every transistor, there is limit on the maximum value for reverse bias voltage. The reverse bias voltage must be within the maximum safe limits. If this maximum limit is exceeded, transistor breakdown occurs. The curves shown at the right side of dotted line represent the breakdown condition. When collector to base voltage increases, width of the depletion region at the junction increases. When VCB increases above the VCB max, increase in depletion region is such that it penetrates into the base until it makes contact with emitter base depletion region. This condition is called punch-through or reach-through effect. When this situation occurs, breakdown occurs, that is, large collector current flows which destroys the transistor. The slope of the CB characteristics gives the four transistor parameters, namely input impedance, output admittance, forward current gain, and reverse voltage gain. They are commonly known as common base hybrid parameters or H parameters. Input impedance HIB is the ratio of the change in emitter base voltage to the change in emitter current with the collector base voltage VCB kept constant. It is the slope of CB input characteristics IE versus VEB. The typical value of HIB ranges from 20 to 50 ohm. Output admittance HOB is the ratio of change in the collector current to the corresponding change in the collector voltage with the emitter current IE kept constant. The typical value of this parameter is in the order of 0.1 to 10 micromho. Forward current gain HFB is the ratio of change in the collector current to the corresponding change in the emitter current, keeping the collector voltage VCB constant. Its typical value varies from 0.9 to 1.0. Reverse voltage gain HRB is the ratio of change in the emitter voltage to the corresponding change in collector voltage with constant emitter current IE. Its typical value is in the order of 10 to the power of minus 5 to 10 to the power minus 4. Summary. In this topic, we have learnt common base configuration, Common base characteristics. Punch through effect.